Yeah, I welcome you again for this 19th lecture on earthquake geotechnical engineering under the module 2nd, which is on dynamic soil properties, and we are discussing constitutive relationship of soils in this module. That is the last chapter of this module, and that is chapter 4 of module 2, and what we have covered are topics which we have covered in this chapter, that is listed here. So, up to the maximum shear modulus we have covered in lecture 18, and in lecture 19 we will discuss only modulus reduction damping ratio curves, which is a big topic and very important, and the next lecture the last two topics will be discussed. So, in equivalent linear models, in this lecture we are going to talk about two things. One is modulus reduction, another is damping ratio. In the early years of earthquake geotechnical engineering, the modulus reduction behavior of coarse and fine grained soils were treated separately. Recent research, however, has revealed a gradual transition between the modulus reduction behavior of non-plastic coarse grained soil and plastic fine grained soils. So, earlier initially what has been done, this modulus reduction curve has been studied separately for coarse grained soil and fine grained soils, but now later research have pointed out that the PI could be an important factor, plasticity index, rather than we divide into coarse grained and fine grained soils. So, depending on the PI value we can have the modulus reduction curves different. So, for example, after reviewing experimental results from a broad range of materials, Dobry and Vucetich in 1987 and Sun et al. In 1988 concluded that the shape of the modulus reduction curve is influenced more by the plasticity index, that is PI, than by the void ratio, and presented curves of the types which is shown in this figure. So, these are the curves, modulus reduction curve, typical modulus reduction curve, which is presented by after Vucetich and Dobry in 1991. And what you could see in this typical on y axis you have G by G max value, which is varying from 0 to 1, maximum value is 1, and on x axis you have cyclic shear strain, which is represented in terms of percentage. So, when the cyclic strain, shear strain in terms of percentage is 10 to power minus 4, then you see irrespective of the PI value all the curves are 1 up to this point. Then as a after this strain, the PI equal to 0, the curve for the sand start degrading and it becomes G by G max start decreasing, while still when Pi equal to 15, 30 they continue. For example, Pi equal to 200 curves, the G by G max value remains 1 up to quite high strain, which is 0.01. So, what we get it here, the shape of these curves for different Pi values looks same. However, later on we will discuss this value where these curves start getting less than 1 value G by G max is called the threshold strain, which will be represented by what we will say gamma TL. For this, for example, gamma TL, this will be for Pi equal to 0, but for Pi equal to 200 the same will be here. So, that means as the plasticity index or Pi increases, then the value of threshold shear strain increases significantly, that we are going to talk again. These curves show the linear cyclic threshold shear strain, which is called gamma TL, is greater for highly plastic soils than for soils of low plasticity. So, it is greater for the clay compared to the sand. This characteristic is extremely important. It can strongly influence the manner in which a soil deposit will simplify, amplify or attenuate earthquake motions. So, because here for the same strain level, like this value, if I draw on this strain level, G by G max value is very much depend on the value of Pi. So, this becomes like almost 0.7 G by G max for 0, but still it is almost 1 for Pi equal to 200 with plastic soil. For Pi equal to 0, the modulus reduction curve is very similar to the average modulus reduction curve, which was specifically drawn for the sands by Seed and Idris, where coarse and fine grained soils were treated separately. So, here Seed and Idris in 1970 they treated separately the coarse grained soils and then fine grained soils, and then behavior, because the coarse grained soils and fine grained soils their behavior is quite different. But Vucetich and Dobry's through this their investigation found that it is the Pi value rather than we say it is coarse grained or fine grained soils that governs this phenomenon. Modulus reduction curve behavior is also influenced by what we call the this similarity will also suggest that modulus reduction may be applicable to both fine and coarse grained soils. Now continue with this. The difficulty of testing very large specimen has been because large specimen, because gravels are the like we can test the soils in the laboratory, normal laboratory, but it is difficult to test the gravels where they are particular for the large specimens. As a result, the widespread testing of gravelly soils in the laboratory is difficult and the data available is very scarce. So, as a result, average reduction curve for gravel is similar to it has been found, but the research have pointed out that the modulus reduction curve which is for gravel is similar to what is for the sand, but slightly flatter. Slightly flatter means they will go more up to this, like if I say that here being slightly flatter, that means they will go G by G max for more range before they start decreasing. Modulus reduction also influenced by effective confining pressure, particularly for soils of low plasticity. If Pi is less, then the effective confining pressure is an important parameter for modulus reduction curves. The linear cyclic threshold strength is greater at high effective confining pressure than at low effective confining pressure. So, gamma TL will be also a function of at what effective confining pressure you are testing, and it is greater if you increase the value of confining pressure. So, when you increase the confining pressure, as a result the G by G max will decrease after at a high strain rather than at low strain. The effect of effective confining pressure and plasticity index on modulus reduction behavior were combined by Ishibashi and Zhang, and as shown in this here. So, this slide is for G by G max curve. So, what in this is in fact giving an equation to how to find the value of G by G max if you know the level of strain, if you know the Pi and the mean effective principal stress. So, here you have sigma m and this k gamma Pi. So, as a result this G by G max, and then so this is the function of 3 parameters, one is shear strength, second plasticity index, and third is mean effective principal stress. And the exponent which is here given from this relation. So, k gamma Pi is a function of strain gamma and Pi plasticity index. The equation long, here it is tan hyperbolic, it is not normal tan, this is also tan hyperbolic in this equation, and which is a function of gamma and Pi. So, when the Pi equal to 0, that is strain for the sand, your NPI will be 0. So, NPI can be directly put in these equations as 0, and in that case this equation is simplified very much. That means, for example, in this equation this term will be over, and in this equation when Pi equal to 0, then this exponent will become 1. So, these equations simplified very much. So, right now this equation is for C phi soil, it could be Pi as well as it could C as well as phi, that means Pi plasticity index could be also there. Then what is the effect? We said that confining pressure is also make effect on this modulus reduction curve. For example, when Pi equal to 0, that means for the sand, for the first case there are 4 curves here which are separate out completely for different mean effective confining pressure. This is for 1 kPa, this is for 50, this is 200 and 400. And as a result, value of G by G max which was 1 here, if you increase the confining pressure, then G by G max will continue to be 1 up to higher level of strain. For example, this was the strain level 10 to the power minus 6 here, but for this curve it will go 10 to the power minus 4. So, that means the value of G by G max will increase for the same level of strain when you increase confining pressures. So, this was the case when Pi equal to 0, that is for the sand, but when Pi equal to 50, all these 4 curves come very close and the effect of confining pressure is almost negligible, particularly at higher value of strain. So, this is the effect of confining pressure. Now, what has been done? that the field test has been conducted, and like laboratory test as well as the field test, and then G by G max. What are the factors? When you increase those factors, what is the effect on the ratio of G by G max? For example, when you increase confining pressure, then G by G max will increase with sigma m, effect decreases when you increase the Pi, which we have already just now seen. Void ratio, when you increase the void ratio, the relative density will decrease. As a result, this G by G max will increase with the E. So, when you increase the void ratio, G by for the when we say the G by G max, that should be considered for the same level of strain, that is the cyclic shear strain should be the same. So, for the same cyclic strain, if I increase the void ratio, then this G by G max will increase. Geological age will increase, cementation will increase G by G max, over consolidation ratio, because OCR G by G max will not affected. Pi, we have seen that when you increase the value of Pi, so G by G max will increase with Pi. Cyclic strain decreases with gamma C cyclic strain. Strain rate, then again, so these are the number of parameters, how they influence on G by G max. Then continue with this. Now normally we have in the cyclic triaxial, as we discussed yesterday in the last 17th lecture, there are two types of tests. One is called stress controlled, another is strain controlled. Under stress controlled harmonic loading conditions, where you put the maximum value of stress is limited, pore pressure generation and structural changes can cause the shear strain amplitude of a soil espacement to increase with increasing number of cycles. So, you have when the number of cycles are increases, with the increasing number of cycles, this increases shear strain amplitude. So, when you increase the number of cycles, then shear strain amplitude will increase. But on another side, when you have strain control test, under strain control test, where you are putting the limit on the maximum value of strain, then in under undrained condition there will be development of pore water pressure, and the shear stress amplitude would decrease with increasing number of cycles. So, in one stress controlled it increases, while in strain controlled it decreases. But here in strain controlled it is stress, shear stress amplitude, while in stress controlled it was shear strain amplitude. So, both are opposite. Here we are considering the how shear strain amplitude varies in the first, while in the second how shear stress amplitude varies. Now, one of the important issue that how this value of G shear modulus varies with the number of cycles when you apply the number of cycles loading. For cohesive soils, the value of shear modulus after n cycles Gn can be related to its value in the first cycle G1. That means first cycle G1 is the value in the first cycle multiplied by the factor delta, where delta is called degradation index, and this degradation is nothing but delta equal to n to the power minus t. What is n? N is the number of cycles and t is the degradation parameter. So, as the degradation parameters like t increases, delta value will decrease. As a result, your Gn will be less than G1. The degradation parameter has been shown to decrease with increasing Pi and increasing over consolidation ratio. So, the value of delta will decrease as you increase the value of Pi. So, that means this degradation will be more for the higher value of Pi. The effects of stiffness degradation on modulus reduction behavior is shown in next figure. So, here is the case here, and this figure is for OCR equal to 1, that means there is no effect on this curve of the over consolidation ratio. On y axis you have G by G max, on x axis you have cyclic shear strain amplitude gamma c. So, effect of cyclic degradation on shear modulus, and this is after Vucetich and Dobry of 1991, and what we see here for different values of Pi, you have like for different values of Pi, here there is a when we understand these curves, this curve is for 0, for the value of Pi 15 there are 4 curves depending on the n number of cycles 1, 10, 100, 1000. For 30 again 1 curve, for Pi equal to 50 again you have the 4 curves 100 and 200. So, the effect of the degradation is done for Pi equal to 15 and Pi equal to 30. So, as you could see, when this curve n equal to 1 is for this curve, so when the value of n is increasing, then you are getting the higher degradation, that is the G by G max decreases. So, this was given by the Hussittig and Dobry. Now, the second part of this we have discussed about modulus reduction. What happens to damping ratio curves for the level of strain? Theoretically, no static dissipation of energy takes place at strains below the linear cyclic threshold shear strain gamma TL. So, gamma TL is the cutoff strain. Below this strain, G by G max remains 1, and when you increase gamma TL, your strain level is more than gamma TL, then G by G max decreases less than 1. Experimental evidence shows that some energy is dissipated even at very low strain, so the damping ratio is never 0. Theoretically, damping ratio should be 0 when you have very low strain, but this is not the case when you have this. So, above the threshold strain, the breadth of the hysteresis loop exhibited by cyclically loaded soil increase with increasing cyclic strain amplitude, which indicates that the damping ratio increases with increasing strain amplitude. So, it has been observed that when you increase the strain amplitude, then the damping ratio increases, because why? The breadth of the hysteresis loop will increase with the when you have the for the higher strain amplitude. See, just as modulus reduction behavior is influenced by plasticity characteristics, similarly the damping ratio is also influenced by the Pi of the soil, and the effect will be shown. Damping ratio of highly plastic soils are lower than those of low plastic soils at the same cyclic strain amplitude. For example, the effect of Pi on the damping ratio is shown in this figure. So, in this figure what you have on y axis you have damping ratio which is in percentage, while on x axis you have the P the cyclic strain amplitude. First of all, for given value of Pi, as the strain amplitude increases, the value of damping ratio increases. So, the damping ratio increases with the strain level of strain, but you get the higher value of damping ratio for Pi equal to 0. That means, for the sand damping will be higher than the clay for the same value of strain, and as the Pi increases for the same value of strain, the value of damping ratio decreases. So, you could see if I draw a line here at 0.1%, then you see that how much is the difference. The difference is very large. Here damping is almost more than 15%, while for this case it is about 3%. So, the sand will have in general for the same level of strain, the sand will exhibit higher damping compared to the clay, while G max it was the reverse, it was more for the clay compared to the sand. So, for Pi equal to 0, damping curve was similar, nearly identical to the average damping curve that was used for coarse grained soils. So, that is okay. Now, continuing with this, the similarity suggests that the damping curves can be applied to both fine and coarse grained soils, because the Pi is the factor rather than we say the fine grained soil or coarse grained soils. The damping behavior of gravel is also similar to that of sand. So, for the we do not have the separate curve right now for the here for the gravels. So, but they could be similar to the sands, and the damping behavior is also influenced by effective confining pressure, particularly for soils of low plasticity. If you have the soils of low plasticity, then that will be also influenced by effective confining pressure. Similar to modulus reduction curve like G by G max, we also have an equation for damping ratio, and in this case rather than the level of strain, this damping ratio is function of, simply if I can write that this is a function of G by G max and Pi. Okay, so only two parameters are coming. However, you have seen that G by G max you need to be known, and in the last equation G by G max was a function of Pi, it was function of gamma, and it was these two factors. So, the gamma, the influence of shear strain has gone in the G by G max, and then once you know the influence of strain in the G by G max, through that the damping ratio will be different at different level of strain. Similar to what we discussed for G by G max ratios, that they are influenced by many factors. Similarly, damping ratio is also influenced by many factors. On the left hand side on this table, the first column says that when these factors are increasing, on the second column says what happened to damping ratio. For example, when you increase the confining pressure, G by G max was increasing, but damping ratio will decrease with effective confining pressure, effect decreases with increasing Pi. For void ratio E, this decreases with increase in E, while this was opposite for G by G max. Geologic age Tg decreases, concentration may decrease with C, over consolidation not affected, it was the same in G by G max, Pi decreases with Pi. So, most of the effect here are opposite what we have seen for the case of G by G max. So, this was about damping ratio. So, we have discussed G by G max as well as for damping ratio how this varies, and with this we have completed equivalent linear models for the soils, and only one chapter one lecture is left for this topic, which is on cyclic nonlinear models and advanced constitutive models. Thank you very much for your kind attention. Thank you.